Okay, I'm going to get started. Today we're going to do agents and tools and how they are built in LangChain and how you work with them. So to motivate this, if you recall, LangChain has this opinionated approach, which is based on chains, where you have a chain of functions and then you invoke it and with the user's input, and it passes through all of the different functions and outputs the result. So this is the simple one: send it through a prompt, get it to the LLM, and then parse the output is one chain. Here's another one, the RAG chain. Get the context from the RAG database along with the question, and then send it to the prompt, send it to the LLM, and then go to the output parser. Okay, so the question is, what happens if a simple chain is not sufficient for your application? What happens if you have an application that requires some form of iteration and reasoning based on the results of any of these executions? And that motivates agents. So if you've heard of agentic AI, that's what this is about. So what is an agent? So an agent takes an LLM and then it adds two things. It adds memory so that it can keep track of what it's doing, and then tools so it can interact with the world to try and answer a user's prompt. So those are two things. And then what happens is that the user will prompt the LLM application. And then what the LLM is tasked to do is to do some reasoning. The user has just asked me to do something, and what I need to do is figure out how to satisfy this request. So I need to, given the tools that I have, figure out an action that I need to execute next in order to try and answer this prompt. So I might invoke a tool. And then in invoking a tool, I might get back a result, and I would want to store that in memory. And then when I get that result, I am going to go and reason about the result and the query and see, do I need to do anything else? And if I need to do anything else, I repeat this step over and over again. And then when I have figured out I can answer the user's question, I will emit an answer down the bottom. So that's what we're going to be doing this week in a nutshell. Okay, agents. This is a definition I pulled out of deeplearning.ai, a program in which the output of an LLM impacts the execution flow of the program. So the LLM is the brain, the program is the vehicle that the brain drives, is essentially what this definition is. This is taking off everywhere. So this is just within the last couple of months. People are like doing stuff like this. We're going to build agents into Google Workspace. So all of your Google Docs and your calendar and your Gmail, we're going to allow you to create an agent that interacts with all of these data sources. You just define these events. Now, it's not going to be at the level that you're going to be writing your agent, but they have some tools, and then you'll give you some programmability without programming a thing. And that's what these folks are doing. This is going to get enabled at Portland State this month sometime. They said January, so soon you'll be able to do this in your own pdx.edu account. At least that's what I'm lobbying OIT to have enabled, but we'll see. So LangChain did this. No-code agents. This was last week, actually. They're like, yeah, you can build your own custom agent, but again, they're going to give you a certain set of tools, and you might need something custom, which is what we're going to be doing this week. Anthropic just released Claude Cowork. So if any of you have been using Claude Code and think that that's like the most awesome thing since sliced bread, they want to build that sort of experience into your regular workflow, not just your programming workflow. And that's what Cowork is. And this got released last week also. It just got released last week, and people are already saying, this is terrible. This is a disaster for security people. And so security people are looking at this and like, oh God, we're in trouble now. You know, we already can't secure the infrastructure, and then you're going to build an application like this and allow anybody to enable it, and then it's super vulnerable to something we call prompt injection, which we're going to cover in 2 weeks, and it's a disaster. But it'll hopefully keep all of you employed for a while, because you'll understand that after week 5, you'll understand the problems, and then you'll be able to help people remediate it. I think that's a pretty good job to target in the next 20 years, I would imagine. Actually, this might be a forever thing because it's prevalent. People are just like rolling this stuff out without thinking about the consequences. And the reason why they're doing it is that the value add of using AI they believe far outstrips any of the risks to the business that a security vulnerability might have. This is why they're taking on that risk, because the benefit is so great. And because the benefit is so great, they're just having people do it. So cross your fingers for the rest of us. Here's one that I really like, N8N. It's an open source agent sort of framework that you can build your own automation. It's basically the open source version of what these other ones are doing. So here's an example this is an example article, and I like this because it comes with an animation. So in this particular agent, you have the ability to chat with the model, you have the ability to send email, you have the ability to get calendar events, you have the ability to search the API, and then this is the interface. You're basically taking all these different tools and then attaching it to an LLM that is able to think about how to use them and execute the tools thusly. So I really like this animation. It is a client intake chatbot. So you have a nutritionist who doesn't want to run a website and doesn't want to sort of like have a real person do patient intake. So it's like, let's do a chatbot. And so this chatbot, if I look at it, it's got the chat, the memory, Google Calendar to get events, Google Calendar to create events, Gmail to send email, and then a feedback form to talk about the experience doing the intake. And so here, the intake is happening. What is your information? And this is getting stored. Well, it's getting sent through the chatbot and then stored in memory. So this is patient info. And then eventually, the patient is trying to schedule an appointment. And so it's like, oh, next Monday. And then it's like 10 a.m. And you'll see that it goes to this get events to get the calendar information. It says, no, it's booked. So then it's like, how about 10 a.m.? And so then 10 a.m. is like there, open, creates the event, sends the email confirmation, and then the next prompt is give me feedback, and then it goes into the sheets to collect the feedback. So this is the kind of stuff that people are adopting in order to replace sort of manual human activity. So this is the power, and this is what you would go into your company and be like, well, what is a workflow that's heavily manual that we just want to get rid of? Like, we don't want that to be done manually anymore. And then you would do something like this, build your own. So I'm working on a course for freshmen to be able to use stuff like N8N. Because it's like, why not? It's like no programming. It's like, you understand Google Calendar, you understand Gmail. Like, why not? So that's basically for spring. I think, yeah, it's CS 112. Well, it's going to be 199, but it's going to be for freshmen. But I think anybody can take it. Okay. The next thing I want to talk about, I'm going to step back and talk about levels of agency, because when you talk about an agent, it's like, well, what kind of agent is it? Like, what kind of powers are we giving our agent? And so this is where the level of agency matters. So these are the kinds of levels that I'm going to talk about very quickly. There's like no agency. You have agency where it's simply making a routing choice. And we've actually done the first two already. That was last class. And then we're going to talk about tool calling agents, multi-step agents, multi-agents, and then the coding agent, or the code agent, which is the last one. Okay, so no agency, it's basically using the LLM as a function call, right? You just send it input, get the output, and then print it out. So that was the first way we used the LLM. The next one, which we also talked about, is to use the natural language understanding function that the LLM has to choose a predefined route through the application. These are pre-programmed routes, and you just say, I'm going to dispatch you to one branch or the other. That's basically a router. So the new thing is, okay, now we're going to have the LLM be able to invoke function calls, to create calls, and then to run them and get the results. And that's the initial thing that we needed for our tool, for our agent that we showed earlier. So here is an example. It's both a router and a tool calling agent. I have two tools above. I have a command interpreter that executes Python in a REPL, and I have a command interpreter that executes Java in an interpreter. And so then I allow the LLM, say, you can either invoke Python or you can invoke JavaScript, and I will run that code that you give me in a sandbox. But you're not actually telling the LLM whether or not it's JavaScript or Python. It's going to figure it out. And so you create an agent, and you allow this execution to happen over here. And then you give it the input, print hello. And this is clearly Python. And so the agent, the LLM looks at it and says, you know what? I know that that's Python. I'm going to send it off to the Riza execution sandbox for Python. And you're going to run the Python code in the sandbox. If I invoke it with JavaScript, console.log, then it knows to fork that off into the JavaScript sandbox, and it runs JavaScript. Okay, so it is executing. It's calling into these two command execution modules to perform the execution of these statements. It's formatting the call, it's running it, it's getting the result, and emitting it back. So that's a tool calling function. Okay, so it turns out most models now support this natively. When you instantiate a model, you can actually bind it with tools, and you have instantly made your model a tool calling model. So in LangChain, it's sort of like a wrapper around the model. And so LangChain is kind of like an interoperability layer so that you don't have to directly bind it to the models. But some examples that you might see out there, just bind it to the model and let the model run. In fact, I actually have a program in the repository that just binds the tools directly to a model for just an example. Okay, the next thing I want to talk about are multi-step agents. And these are the agents I kind of showed you in the animation. So I'm going to first talk about kind of a system that led up to this. So back in 2023, there was this automatic reasoning and tool use. And the idea is to allow that LLM to generate and orchestrate tool calls in order to solve a prompt. So here's an example. I'm going to give the LLM 3 tools. You can search the internet, you can produce Python code, and you can execute Python code. And I'm going to have you take a user's prompt and figure out how to use those 3 tools to answer this user's query. So then the LLM generates the multi-step reasoning plan based on what the user has asked for. And then so it's basically going to be generating the plan and executing it. Whenever it stops, whenever it needs to stop and execute an external tool, it will pause, and then we'll call the tool, wait for the results, and then continue. So when the responses come back, it takes those responses in, and then resumes generation of the code. So here is an example of how that they use in this paper. So the task is to translate into Pig Latin this input, Albert goes home. So this is the user prompt. And then you're going to give this to the agent, and the agent needs to satisfy this prompt. And so it has no idea how to translate Pig Latin. So it does a search. How do you write English as Pig Latin? And then the response comes back. You add yay if it starts with the vowel. You switch the letters if it begins with the consonant, and then add a at the end of that. And so then it writes code. It says, okay, I need to now generate the Python code that can translate Albert goes home into Pig Latin. And so this is the code. This is the Python code. For each word in Albert goes home, I am going to see if the first letter begins with A, E, I, O, U, and then I'm going to print that out and do yay, and then the consonant one does some character swap. And then the result, I'm going to take this Python program and execute it, and then get this as a result. And now I have the answer, and then this art agent will then spit out the answer. So that's like one of the initial approaches for doing this tool execution. Okay, so this is the prompt that is used to configure the LLM. So the LLM is just natural language. There's no magic here. The LLM is taking natural language, but then it's formatting tool calls and then doing the execution. So the prompt, the program that sort of configures this behavior is here. So here is your question, and this is the user's question that comes in. You have access to these particular tools, which will be those 3. And then the instruction, the background instruction for the LLM is that you must reflect the next thing that you do with the thought, and then you fill in your thoughts on how to address this user's question. And then after that, you can either call a tool or you can say, I know the answer, and print your final answer. So that's the template. So here's an example. How many seconds are there in 1 hour, 23 minutes, and 45 seconds? And then here's the prompt, the background prompt. Say I have these tools. I've configured my art agent to have the convert time tool. And this converts time in this format, the exact format that has been given, hours, minutes, seconds, just into seconds. And so then this is basically the template that you give the LLM and say, execute. And the LLM looks at this and says, oh, I know what to do. I need to convert the time string into seconds. So we prompted the LLM to generate the thought. The thought gets generated, and then the next thing that the LLM has been asked to do, and I don't have the action prompt here, but there's more to that prompt than just the first 3 lines. It also has been prompted to generate the action that would call the tool, convert time, with whatever that input is, and this is what the LLM produces. I need you to invoke the correct time convert time function with this as the action input, and that does the function call. Okay, and then the result comes back, and it's 5,025, and then this can get returned. So then it has to think, now that I have that observation, I now have that information, and I can return a final answer. Okay, so this is a precursor to the agent loop that most everything is using now. This is called the Reason Action Agent, or REACT. So this is basically chain of thought reasoning with actions and observations. And the idea is that you ask the LLM to just keep on running a program to itself until it finds the answer. And so initially, there were these reason-only systems where you're just producing a reasoning trace. And then there was action-only systems. Well, React is doing both. It's doing a reasoning trace along with the execution and observation in a loop. This is what it looks like. And this is very similar to what I had shown you in the original figure. I have a thought of what to do. I'll take an action. I'll get the observation back. And then I'll take in that observation. And then I'll have another thought. And if the thought is, I know the answer, then I just emit this final answer. Okay, this agent is typically used in conjunction with tools that access the external world. So this is a figure, a little bit more of a detailed figure. You get the prompt from the user. The LLM does a reasoning about it. It parses what the next thing to do is from this output. If the output says, I know the final answer, I just emit it. If not, then if the output has a tool call, I'll call the tool that accesses the external world. I'll get the results back, and then I will re-reason about this trace to figure out what the next step is. And I keep on doing this in a loop until the output that the LLM produces says, I know the final answer, and I'm going to emit it. Okay, this is the React prompt template. It's very similar to the other one, but it's actually sort of giving you the format of the function calls as part of this prompt. So here is an example that uses Wikipedia and calculator. So, and it really helps. So the reason I'm showing you this in gory detail, this might be the last time you ever see a React prompt, because now you'll just end up using it. But in order for me to teach you the prompt injection into this, you have to know the underlying format that the LLM is using to think. Because a prompt injection attack is you jumping into the LLM's thoughts. And so if you know the format of the LLM's thoughts, you can put voices in the LLM's head. That's prompt injection. So that's why I'm teaching. That's why I'm like, this is a gory detail of the prompt. Well, this is what you're going to be attacking in 2 weeks. So keep that in mind. So here is the React prompt template that's instantiated with 2 tools. It's a Wikipedia tool that allows you to search Wikipedia, and it's a calculator tool that allows you to do math. And this prompt template is specifying exactly how tools need to be called. So here you say you have to invoke tools by specifying a JSON blob, the JSON blob should have an action key, and it should have an action input key with the parameters to call that action. And this is the format of this. And so you're saying, please format a call like this. And then what's happening is the runtime system is just going to execute that blob as is from the LLM and invoke that call. Okay. And then this is how I want you to think, is the next part of this prompt template. Always use this following format. Start with the question that you must answer. This is the goal. And then always have a thought, what you need to do next. Always have an action, which is either a JSON blob to invoke next, and then an observation, which is the results of that action. Now, what you're going to do is, as you're executing these actions and getting these results, you're just appending to this prompt template. You're basically giving it the full execution trace so that every iteration of the reasoning, you can figure out whether or not you're done. You're progressing and getting more information as you go along down this template. And then eventually you'll have to say, I know the final answer, and that's here. The final answer is at the bottom. Okay, so that's the whole prompt template. And so if you can fake out any of this stuff and confuse the LLM into thinking, for example, if I just say, yeah, your final answer is, what's that number, 42? That's the Hitchhiker's Guide to the Galaxy. That book's too old for you all. So there's this book, what is the meaning of the, what is it, the meaning of the universe? And everything is, the answer is 42. You could say, well, I'm going to inject that into somehow into this reasoning trace and then make you emit 42 all the time. So that's why I'm showing you this prompt format. Okay, this is you're like, wow, really? Is that how it works? It's that easy to confuse an LLM? It's that easy to confuse an LLM, which is the problem that we're facing. Okay, so here's an example execution. This is super old. This was back when Joe Biden was still president. So this is what we're going to use, though, because like, well, somebody went through all the trouble into making this, and it's a pretty good example, so I don't want to throw it away. So you have the Wikipedia, you got the calculator, you've got the React prompt template here that I just showed you. And then I prompt it with this thing in red. So the red comes from the user. And then, boom, the next thing I'm asking the LLM to do is to have a thought. What do you need to do next? And then that goes to the LLM. The LLM says, oh, my thought is I should use Wikipedia to find the current American president's age. So that's the next thing. And so I need to format an action to call Wikipedia, and the input parameter is, what is the current American president? So I invoke that tool, and that tool goes out to the internet, gets the information about the current American president, and then in green is the observation. And so the observation comes back right here in this one down here, and it says, oh, it's Joe Biden is Wikipedia's answer. And so then I can fill out the next part of it. So the next thought is, I found the information about the current American president. It's Joe Biden. And then the next thought is like, well, I need to find Joe Biden's age. And so then I format another action to Wikipedia. The action input is Joe Biden, so I can figure out when he was born. And then that goes out. This goes out to Wikipedia, and then I get the response. And then in green, the age comes back, and the age is 79 at that point. So you can figure out how old this example is. And so that comes back in green. It's like, I found Joe Biden's age. Now I just need to multiply his age by 82. And so then I format a calculator action. And I say, what is 79 times 82? And that invokes the calculator tool. And that generates the response. The response comes back, and it's 6,478. And then now the LLM's like, well, I know the answer. There's nothing else to do. So now I can say, I know the final answer colon, the current American president's age is that. Okay? So you see the format of the thinking and the observations and the actions, and you're like, well, that better be secure. Otherwise, the agent's going to mess up. It's going to do something else. Okay? So there is some trust there, and that's how agents work. Any questions about this? Yeah.
How trustworthy is it to limit the number of times?
So at the beginning, I always put a limit of 8. on all of these agents. So if you have a runaway agent, yeah, you're goodbye tokens. And I had some students, I mean, literally they had thousands, especially if you haven't done a good job with the RAG. This is why I do the RAG section first, because if you have an agent in a loop sending the Portland State catalog back and forth between the model, you're gonna spend a lot of money. And so this is where the engineering comes in with that. Any other question about what we're doing? You'll get a lot of experience with this because that's basically all of this week is messing around with agents. Any other question? All right, so in LangChain, there is a sort of a class, a LangChain agents class, and it's basically a library of all of these different ways of building multi-step agents that combine tools, language models, and reasoning in a loop. We're mostly going to use one or two of these things, but just know that there's a whole. So for your homework, you can experiment with whatever you like in that, in terms of doing something different than what's in the labs. You can explore to your heart's content, or you can build an agent that does some other different kind of application than what's in the repository. It's up to you. So this is just the week of LangChain agents. So here's an example of instantiating an agent. So in this agent, I'm going to give it the search API. So this is an interface to Google's search results. I don't know if you've read the news, but they're getting sued by Google because what they do is they basically do a whole bunch of Google searches and cache the results and then sell it, resell it for people like us doing LangChain apps and don't want to interface with Google. So that's basically what SERP API is. But we're gonna use the tool. Well, I don't think, yeah, we're gonna use the tool this week. So in this case, we're gonna do the SERP API and the LLM math. I think I had you set up an API key for this because they are charging you for this if you do a lot of them, which is why Google's not very happy with them. And so then I'm gonna say, these are the tools I want the agent to have. I'm going to instantiate an agent which has access to these tools. And then what I'm going to do is I'm going to invoke the agent and say, tell me who is Leonardo DiCaprio's girlfriend and what is her current age raised to the 0.43 power. And if you enable the verbose mode, you can see the execution trace. And I would recommend for you at the beginning to always look at the execution trace to get an idea of what the limits are for LLM thinking. It might be way better than when I last tried this, but you always need to know the boundary of what the LLM can reliably do. So it might be awesome now, it might never make a mistake, but you should know when it does, where it makes these mistakes. So I have dumped out the verbose mode on this execution trace for this agent. And so this is the thought. The first thought is I need to find out who Leonardo DiCaprio's girlfriend is, and then do the age. And so the first thing I'm going to do is search for his girlfriend. I get back Vittoria Soretti, and then the next thought is like, I need to find out her age. So I'm going to do another search. What is her age? And I'm going to get the result back. It's 25 years old. And then I create another thought. I need 25 raised to 0.43, and I have LLM math, which is the calculator. And then I can do that calculation. I get the observation back. And this is where my thought is, well, that's the answer. I know it. So now I'm going to return final answer. This is her information. And then you finished. And then that's what you emit as the result of this agent. Okay. So it's like the deep dive into what the agent is doing underneath. So one of the things with agents is that it's only as good as the tools that you give it. And one of the reasons why LangChain took off is that it had a whole bunch of tools that they implemented. It's kind of like the document loaders, where like, yeah, they implemented a whole bunch of transformations from whatever document you have into text. And so they did the same thing with tools. All of these different powers that you want to give an LLM, we're going to build into LangChain's ecosystem. Now, we'll talk about this next week, but eventually, those powers that the LLM are given access to, we're going to allow you to host those actions over the internet. That's what MCP is. So we're like remote tools is basically next week. But if you are looking for a framework that has a whole bunch of local tools, and a library of local tools for you to utilize. That's in LangChain tools. Okay, so these are just a list of tools. The terminal tool, the file system tool, Google search, GraphQL, Dolly image. I mean, there's a whole bunch of these things. And if you want to utilize any of these tools as part of your homework for this week, you're more than welcome to go crazy. Find stuff that you want to use in the built-in tools. Also find some that are like, or also create some of your own for things that you want. Like maybe you have a personal project and you want to create a tool that helps you with your own personal project. I do recommend those, because if you get asked about it, you can say, oh yeah, I built this to solve my problem. That looks good. When you're getting interviewed and you're like, oh yeah, I just happened, I had this thing I needed to automate, I built the tool to do it. That actually looks good for you, actually. Okay, so another thing that LangChain provides is a library of what they call toolkits. Toolkits are just collection of tools that are related to each other. So one of the toolkits that's there is a toolkit based on querying SQL databases. So if you have a bunch of actions that you want to enable an agent to invoke on your database, you can use the SQL database toolkit. So here's an example. Let's say I'm going to build a natural language interface to my database. And so I've heard this in companies. It's like there's a database admin in the company, and this admin is always being asked to get information out of the database because the rest of the company doesn't know SQL. And so this is perfect for that admin, because they're like, okay, now I don't have, they just like text it or enter it into a chat bot, and then I'm good to go. I don't have to deal with this. So here's an example of what you would have. Is like, how many customers do we have in our database? Now with the toolkit, there are built-in tools that are provided when you import the SQL toolkit package into your agent. So these are just 3 of the tools in the toolkit. There's a list the tables in the database. There is a show table schema tool, and then there's run an arbitrary SQL query. Now this is super dangerous. You shouldn't actually have that, and we'll talk about secure tool design. In fact, you'll look at secure tool design in your labs. You'll be like, well, somebody could just wipe out the database using my chat interface. You're like, yeah, if you say, please, agent, drop tables, yeah, your database is blown away. So you'll be doing that in your lab, and then you'll be like, yeah, let me write a better set of tools so that the user can't drop the database. So that's one of your exercises this week. Okay, so we're going to have this query that we want to answer. How many customers do we have in our database? I was like, okay, my thought is when it comes to databases, I have 3 actions that I can choose from. These are the 3 actions. I need to start by getting the names of all the tables, because I don't even know which table the customers are stored in order to figure out how many customers there are in that table. So that's the first one. And then I call that, and I get back, there's 3 tables. There's agents, customer, and orders. And it's like, cool, let me just query the customer table, but I don't know the columns in the customer table. And so then what I need to do is I need to query the table schema for the customers table is the next step. So I invoke an action, SQL database schema, action input is the customer table. And then I get back, oh, this is the customer table, the code and the name and these sorts of things. And so then the agent's like, well, I know the format of the customer table. Now I can just query the customer table to get the number of customers in that table. And then it produces the SQL query, which is select count star from customer. And it actually probably didn't need that SQL database schema call, because it's like, why couldn't you have done that initially once you found out the customer table? But oh well, the agent sometimes doesn't do the same thing a human does. And that's something you'll definitely come across this week as you are writing your agent, trying to get it to, you're like, I know what I'm thinking of when it comes to an action trace, and you'll see that usually the agent doesn't really do what you expect it to do. And that's the learning for this week. And then it comes back, you got 25 rows. So 25 customers, and then the final answer comes back. Okay. So that is React. Questions about React and the tools? Yeah. Oh, yeah. all the time there are wrong answers. In fact, it's hilarious. I have this high school student who's like, he's like uber, intelligent and productive. He was like running a trace, and he was like, oh yeah, I was asking him for a trace to show execution, and he ran the trace, and it looked like the agent worked. And then, but like, I was like, do the tool calls, and the tools fell off like one step before the actual answer should have been produced. It had fabricated the last step. So, and you have no idea when it's like, I'm going to fabricate this because that last step is so hard. I don't think I can do it. So then, like, because you didn't tell it not to fabricate anything, and this is where you have to be very specific, it fabricated it. So this is where the prompting really matters with the agent. So there isn't that precise of a, like in the prompts that I showed you, there isn't a precise instruction to say, don't fabricate anything, only use the results of tool calls. But that could be something you add in there. And that's merely a suggestion to the LLM. That's no guarantee that it won't ignore that either, because there's a whole bunch of things that you're giving this LLM, and it can't say yes to everything usually. So it'll say yes to the things that it thinks you want. It's trying to please you. And so if it thinks it can please you by making something up, it'll please you by making something up. So this is why, in fact, in the database, so this week's labs, I actually have you run the SQL queries to get the actual results, the ground truth, before I have you interact with the agent, because then you'll know when the agent's just making stuff up. So that's hopefully, that lab hopefully works. That was because in prior versions of this, it would just make things up, and then because I didn't have students actually figure out what the ground truth was, they were like, oh yeah, it all works. And that's the worst thing that I can leave you with from this class, is say everything worked. That's what I'm trying not to do. Like, yeah, it does. You have to check everything because everything won't all work. Okay. So now I'm going to talk about alternatives to React, and this is going to motivate some of the later labs. So there are issues with React. One thing is that every every tool call has to be generated from an LLM call. I have to think every time and then say, this is the next tool. And then think again, ask the model again, and then this is the next tool. Okay, so it only plans one subproblem at a time and is doing step-by-step execution. The other thing that's happening is that you have this serial blocking execution of each tool invocation. Let's say you already know you need 3 tool invocations. Well, if you just do one and wait for the response, then the other 2 can't execute. That's another issue with the way React is working. So this motivates a class of agents called plan and execute agents. So this is the first one, plan and solve prompting, or they call this baby AGI. And so there is a walkthrough. This agent actually has a LangChain implementation if you want to do this style of agent. So the idea here is that the user is going to come with a request, and then I'm going to ask the LLM to create an entire plan for how I'm going to answer this user's query. Not just the next action. I want the whole plan. So like that Joe Biden thing, I'm like, yeah, find out who the current president is, find out the age of the current president, calculate the age times 82. All that stuff could be generated with one call. There's no reason why I had to do a step-by-step generation of that tool call. That's what this is doing them all at once. Okay, so then the planner prompts the LLM to generate a multi-step plan ahead of time. And then it dispatches all of them and says, go ahead and execute every task in this task list, and then update the state. When these tasks finish, go ahead and update the state. And then if I need to redo my plan as a result of the state that gets passed back, I will rewrite this list on task sort of completion. Sometimes I don't need to rewrite the task list, but you have an initial plan, but maybe the result of one of the tasks completely redirects what you should do next. And then you have to like tear up the task list and generate a new task list. But the important thing is that if that task list doesn't change, then it was only one LLM call to do that entire plan. Okay, and then respond to the user after. One of the nice things about this architecture is that all of these things, these tasks, these could be done concurrently. They could be spawned off asynchronously. So if you're a JavaScript programmer and you know asynchronous programming, and none of these tasks rely on each other, like if the task list, and you'll be doing this in your lab, the task list is to take the NBA headlines, the NFL headlines, and maybe the MLS headlines, then I could have a task to do each one of those and then spawn them off in parallel to go retrieve those headlines. I can do that with this. I can't do that necessarily with the React loop. Okay. Okay, this is the details of the plan and execute prompt template. I'm not going to go through here, but you can read it for your enrichment later, just to give you an idea of how this thing works. Here's another one, reasoning without observations. And the idea here is to also avoid these per task LLM calls. So again, it's similar to the other one. You have a planner, you generate a task list, and in this task list, you explicitly identify what the data dependencies are between the tasks. So some of these tasks, so for example, so this is where you're identifying the variable that might come back after you retrieve one of the tasks. So this is what the reasoning without observations is doing. It's putting placeholders to get the results of each one of these calls. Okay, so then it asks a worker to execute the tasks in this plan. And then the worker will execute these things. And then the result of executing all of these tasks will get, so you execute every single one of them, send it to the solver, and then in one batch, the solver will evaluate the output and then send it back to the user. Okay, so there's less iteration on this particular one. It's just do all the tasks, produce the results from those tasks, and then evaluate this thing. Okay, so here's an example that they use in this paper. What is the name of the cognac house that makes the main ingredient in the henchata? So I don't know, I don't drink, so it's like, yeah, hard liquor, I don't know any of this stuff. But this is the plan that gets created. The planner's like, well, I need to first search for more information about the henchata, and the answer I'm gonna assign to this variable E1. And then I'm gonna take that variable E1 and I say, what is the main ingredient of find out the main ingredient of whatever's in E1. And the result of that is stored in E2. And then the next step of the plan is search for more information about the main ingredient E2, and the result is E3. And then finally, find the cognac house that makes the main ingredient, E3, and then the result is E4. So the planner generates that all in one shot. And then it says, go execute that plan and give me the results of this. And so then the worker takes all of this, and some of these things have to be done serially, right? Because this just happens to be the case where you need the one to pass to the other, so it can't get rid of data dependencies. But if they could be done in parallel, then this system could do those tasks in parallel. So here's an example, the trace. So you figure out that the cocktail consists of Hennessy cognac, and then you ask about Hennessy cognac. What's the main ingredient? Oh, no. What is the main ingredient of? Okay, let's see. What is the main? So you get back Hennessy cognac, and then you use Hennessy cognac to look for it, and then you see that this company makes the Hennessy cognac, and then finally you get that result back, and then this is the result. The answer is this company at the end. Okay, so then this is done all at once. This is all done, and then the results are passed to the solver, and the solver gets the execution trace and then generates the answer. Okay, and then the answer is that company. Here is the prompt template for that. So again, based on the agent that you're running, how you attack it, how you inject into this prompt is different. So that's why I'm showing it to you, but I'm not going to walk through here. This stuff is very similar to the other prompts. I do have an execution trace here. So just to show you how the prompt works, what is the hometown of the 2024 Australian Open winner? And then this is the plan that gets generated. Well, you have to search for who won the 2024 Australian Open. And then from the results, what is that person's name? And then from that result, you say, what is the hometown of that person? And then from that, you can answer the prompt. So those are the 4 steps on that. Okay, and then that gets executed, and then the solver prompt says, that's the result of the execution, answer the question based on those results. Okay, so the last one I want to talk about is LLM compiler. And again, these are all very similar to try and address the same problem. So the idea here is to not only reduce the LLM calls, but to enable parallel execution of your task tree. So LLM compiler has the same kind of operation, but rather than doing a list of tasks, it tries to represent your task list as a DAG. So it's trying to describe the data dependencies in your tasks so that they can be executed in parallel if possible. So you create the DAG where different parts of the DAG that are sort of can be executed in parallel. And then it dispatches this DAG into a task execution unit, a task fetching and execution unit. And this is where the DAG, you have to execute A, and then the results of A can be passed to both B and C in parallel. And then those 2 tasks execute in parallel, and then you wait for the results, and then you can return the results. So this is your last lab of this week, is doing this for the NBA and the NFL headlines. I'm going to be like, hey, I need my sports headlines. And then it says, oh, get the NBA ones, get the NFL ones in parallel, and then collect the results, just to show you. So we're building this in something called LangGraph. And if you look at this, it's like, that's a graph. Why don't I build a graphics abstraction to build it? Well, that's what LangGraph is. So I'm giving you a preview of that. And this is the exact example, like NBA, NFL, and then like get the headlines for both is effectively the hello world of LangGraph. Okay. So yeah, the benefit of this kind of pattern is that you can get better concurrency. Okay, and then in this particular one, you can recompile based on the results of these tasks as well. So so in my application, it is static, but like this doesn't necessarily, the graph doesn't necessarily have to be a static thing if you believe you can re-optimize based on the results of a prior execution. Okay, so this is the example that they give. I want to do a market cap query, and it says, how much does Microsoft's market cap need to increase in order to exceed Apple's market cap? So then the compiler's like, well, I need these tasks. Search the internet for Microsoft's market cap, search it for Apple's, do some math, and then send the result to the LLM. So 1, 2, 3, and 4, and that's the DAG. And then this is going to get mapped, sent to the task fetching unit. And then this is where the execution can be done. So you could do the first 2 in parallel, and then that feeds into the 3rd one, and then that feeds into the 4th one in serial for this particular example. Okay, as before, there's a prompt template for you to see how it formats all of this stuff. I'm gonna skip it, but it's something you can look at if you're interested in. Okay, one of the critical things about tool calling agents is making sure your model has the ability to generate JSON that actually works, right? And that's asking a lot. So you think that the LLM can do some magic 100% correct function calling, but it turns out that's not necessarily the case. And so there are these benchmarks. They call them function calling benchmarks. And so when you come across them, the reason why these are so important is because if you have an LLM generating your function calls, it better do well on the Berkeley function calling benchmark. So this is their leaderboard. And then you can see the latest models. And not only, the one thing I like about this leaderboard, it's not only the accuracy, but how much it costs you. So you do pay a premium. So companies are paying a premium for function calling models that are accurate because the cost of making a mistake is too great. So then you can see, well, how much benefit am I getting for the extra money that I'm paying And so this just came out from last month, so it's relatively recent. But this is the kind of thing that you need to be aware of when you're building agents. Is like, well, which model should I use for my agent? And so when you're building your agent, if you do have API keys from other vendors, or if you want to switch to different models, if you think your agent is going off the rails too often, you can go to this leaderboard and you can even look at all the different Gemini agent the models and see which one's got the best function calling one. Especially if you look through that trace and you see that it's formatting a call incorrectly, well, then you just find a better model. The other thing you can do is to try and be more precise in your instructions as well, and we'll talk about that next week, actually. Okay, so the last thing I want to talk about is code agents before I take a break. So this is the highest level of autonomy. And so with code agents, we're going to allow the agent to produce the code that gets executed. So before, we were allowing the agent to craft the function calls, but we created the function calls, right? We gave it those function calls. But now, if you want a code agent, you're like, no, you create the Python, and I'm just going to allow you to execute the Python. So this is really living dangerously, because yeah, it could craft os.system rm-rf, and you're done. Or it could be tricked into doing that, and then you're done. This is why agents are dangerous. It's like if somebody is able to inject rm-rf onto your agent, you have a denial of service attack. So, but this is the carrot. Everyone's like, oh, wow, this would be so great if I did this. So they will be like, yeah, let's do a code agent. So here's an example. Your task is to determine the most cost-effective country to purchase a smartphone. There's like 4 countries, USA, Japan, Germany, or India. And let's say I have a multi-step tool calling agent, and I have 3 tools. Get the phone's price, get the exchange rate, and then convert and tax the phone. Those are the 3. And I have 4 countries. And I'm like, I got to do 12 calls. I have to do 12 LLM calls. I have to do 12 function calls. And I'm like, that's expensive for this operation. So a code agent could be like, you know what? I can just create this Python loop. And I'll be like, I'm going to call all of this in a loop. Get phone price, get rate, convert and tax, and then be done. So that's why you would do a code agent. It was like, yeah, those tools, the level of abstraction at the tool level is too coarse. I need a fine-grained access to the Python REPL. So you give it the fine-grained access to the Python REPL, which is basically what I'm having you do for all of your agents. Because I want you to inject into I want you to compromise your own agent just to show yourselves how dangerous this kind of stuff is. I showed you right at the beginning of this class, the Riza sandbox. This is why that company exists. It's like if you are allowing a code agent to operate and you want it to execute in a safe environment that doesn't have any of your secrets in it, you would use their sandbox. That's their business model. So that's what they want to do. They want to be the detonator for your LLM's crappy Python. No, it's probably better than your own, but your LLM's good Python code is basically what they're trying to do. Okay, so I am going to take a break. I'll do a 5-minute. Yeah, I'll do a 5-minute. 6:30. I'll start back up with the rest of what I'm going to talk about today. Okay, I'm going to talk about reasoning models. So we talked about reasoning tasks in week 1, and you have all of these tasks that you tried to get an LLM to do, and some of them were better than others. But what we're just asking the LLM to do now is pretty substantial, right? We're trying to get the LLM to think like a human. And I'm like, what in the world do we think we did to allow the LLM to do that? It's not obvious. And in particular, some of these initial models were terrible at it. And your mileage will vary when you execute these agents. And specifically, initial models were built for text completion. and not necessarily reasoning step by step on a task. As a result, there are these planning benchmarks that got developed to try and get models that very specifically were good at reasoning. So here's an example where they're like, we have these different domains. Blocks world is like the common one. Can you reason about solving problems in these benchmarks? And so the question is can you build better agents if you used a model that specifically has been trained to reason? And so for a reasoning model, you don't need the whole corpus of Shakespeare, right? It's like, do I need that? You're like, no. Why do I have the model that knows about Shakespeare, the whole corpus of Shakespeare, doing my reasoning task for me? Why don't I have a purpose-built reasoning model? And so that leads to, and this happened a couple years ago, this led to something called Strawberry, OpenAI Strawberry. They were like, yeah, we have ChatGPT. It's super good at generating text, completing text, but we want to make it really good at reasoning. So we're going to focus a lot less on training the model on data. We're like, we don't need the text regurgitation. We're not going to focus on that. But instead, when it is asked to do a task, we want to focus on inferencing, which is sitting there thinking about what to do next. Okay, so the idea is that we need models that think before answering. So if you remember, like, back in grade school, like you memorized like answers to questions, and then on a test, you just boom, 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 straight up regurgitation. And then you get to college, and they're actually asking you calculus problems. And you're like, oh, I can't memorize the answers to that. I have to sit there and reason about it. That's the difference between the initial models, which were just memorizing and regurgitating, and reasoning models, where you're like, I got to do something a little bit more sophisticated. So this is what they did. They were like, yeah, most LLMs initially were doing a whole bunch of training on the left, the gray and the green, and then spending a tiny amount of their budget on inferencing. This is when the user prompts the model. That's the amount of compute that gets allocated for answering the prompt. So a whole bunch of compute for training, a tiny bit for inference. They're like, let's flip that. Why don't we do less training, and then we'll put all the inferencing costs, we'll crank that up, especially for reasoning tasks. And so when this got released, a lot of my students were like, let's use like the ones that could afford the OpenAI key. We're like, I'm going to build my agent on that because I need more thinking in order to get my agent to work. And so inevitably, all the people who are using O1 got better agent results out of their agent. So you might find O1 doesn't exist anymore. But one of the things that OpenAI has allowed you to do is specify the budget for inferencing. So if you have a knob now that you can say, I want more inferencing time to be spent so I can make sure this result is guaranteed to be correct as much as possible. Okay, so so the idea is to factor out reasoning from the knowledge base. So the gray and the green is all about the knowledge base. So we're like, yeah, we don't need that as much anymore. We just need the reasoning. And then we'll just bring the knowledge in a RAG application. I will bring you the knowledge, but you need to just reason. So that's where some of this model design has shifted more towards reasoning. Okay, so here's an example of what you could do. You could do something like the tree of thoughts. You're like, well, I'm going to have this model spawn off a whole bunch of different ways of solving a problem. That's the tree of thoughts. And then I'm going to coalesce these things to produce the final output. And by doing so, I'll produce a much more accurate result. So that's the idea. And this is not cheap. You're just investing more time in this. So one of the things that was also happening in prior versions was that the time of day mattered in terms of the amount of inferencing budget you were afforded your model. And you still might run into this today, because during the afternoon, it's hard to get a model to reason for you because everybody is using the model to do reasoning. And so your budget, so it's the same model, but the amount of time it gets to think changes the results. This is why it's non-deterministic. So you might get better determinism if you were running it on your own hardware, the Olama stuff, because at least that you're actually fixing the CPU budget. Okay, so then the result is you give it more time to think, it does better on the benchmarks. So you see all this O1 is kicking butt. It's like it's better than the human expert. So there's this, as soon as it's better than the human, you're like, yeah, let's not have the human do that anymore. And this is one of those things. It's better than the human at doing these things. You're like, oh, okay. And this is, yeah, PhD level science questions. You're like, Okay, so that all sounds good, but the opinions are very mixed. So this is Apple putting out a study saying, yeah, it's not really doing genuine reasoning. It's just mimicking the reasoning steps it found in training. And that's always been the drawback in this transformer sort of architecture for these models. It's just it's doing a next predicted reasoning step all the time. And if it hasn't seen a reasoning case for the example that you want it to reason about, it won't give you the right result. And this came out a couple days ago. Wait, what day is today? This came out yesterday. This came out today. I put this in there today. This is Google's, actually, he said this a couple days ago. I put the headline today. This is the commentary that the DeepMind, so DeepMind is where all of the transformative AI stuff, this is where the transformers came out of, the DeepMind. And it got spun out, and then ChatGPT, OpenAI actually was, took that technology and ran with it. So this is the DeepMind CEO. And they're like, the next token sort of statistical sort of prediction thing, there is a limit to that. And this is what's driving all the models right now, is that it's basically doing prediction. And it's not actually reasoning about the world the way humans are reasoning about the world. So you need this. So I know Amita in our department, she's looking at neurosymbolic reasoning. It's like, yeah, that's kind of the way you want it to be done, rather than memorizing, mimicking a reasoning task. You actually want it to do the reasoning on the other end. And so this is a quote from the DeepMind CEO. It's like, invention requires the ability to run thought experiments, reason from first principles. This is not what the current LLMs are doing, reasoning from first principles. And this is why it has trouble actually doing something new, because it can't take those first principles and apply them unless it's seen them. And then it's not really doing, it's not really innovating, it's just copying. Okay, we're gonna find out. You're gonna basically use this and say it's good enough. So it's like anything, it's like, as long as it's good enough, this is why we have Starbucks. And yeah, that coffee's good enough, I'll just drink that. So we'll see, like if OpenAI is good enough for, or if the current models are good enough. I know that DeepMind is doing a lot of sort of non-transformer based models for this particular task. So they believe the next jump is to go away from transformer models and to do true AI. So that's an aside. Okay, the next thing I want to talk about is LangGraph. So LangGraph is a framework for building stateful multi-agent applications. LangChain can only get you so far. It can build simple applications like I'm having you do in this class. But eventually, you want to coordinate large sort of operations, multiple operations, and multi-agent operations. And so in order to take advantage of that, this is where the graph-based model has been developed. So one of the things with LangGraph is that if you saw in previous examples, you have tool calls that could be done in parallel. And so one of the things LangGraph enables is the easy specification of parallel execution of tasks. And we'll look at a simple example later. The other thing is that if you have an application where feedback from parts of your application are fed into other parts of your application and changes execution, this is often best expressed as a graph, right? As a cycle of components in your program that give feedback to each other. So it's kind of like a state machine, since we're in the CS department. It's like, yeah, if you can architect your application as a state machine, and we think like people with I mean, that's how we do our programs as state machines, then that's the best way to express an LLM application. Okay, so this is easily supported if you can express your workload as a graph. So here's an example, a self-reflective RAG application allowing self-correction. I have this RAG application, and rather than being just a chain, which is what you saw before, I'm going to allow this feedback loop to say, I'm going to look at the answers, feed it back into the application, and allow it to correct itself. Maybe I can change its operation. And so then this can be expressed in the graph and then sort of deployed in a concise way. Okay, so here are some graphs. Here's one, and you can build some of these for your projects if you want. An agent supervisor. You have a supervisor agent that spawns other agents and then uses the other agents as tools and then kind of coordinates the results and collects them up. So the canonical one that I've seen in LangGraph is a research assistant. So maybe I need to have a stock market research assistant. Maybe I have to have a company lookup research assistant. Maybe I have to do some other news article research assistant. And I'm going to spawn those 3 agents off to do my research. And then they're going to come back and I'm going to basically coalesce them in the supervisor. So that can be expressed as a graph. So here's another one. Maybe it's a hierarchy. I have the research agent on the left branch, and then I could actually produce a report. I'm going to do all the research. This is like if you ever have to do a term paper in the rest of your career here at Portland State. If somebody asks you to write a term paper, you could do this. You build it as a LangGraph application. Yeah, research, these are my sources, and then I'm going to build an agent to do the document authoring. If I only had this when I was a sophomore in high school, I remember that was my most traumatic experience, is doing a term paper. But now I could write a program to do it, and I won't have to actually do the typing. So this is what you could do. You could actually write a term paper generator. And then schools that are actually having their kids do that, you could sell that software to the kids to have that generate. Just saying, if you're all looking for a business model for a company, there's lots of people starting companies up. That would be a good one. Okay, so here's an example of a simple LangGraph. So I try and do examples that I can fit in slides. So here's one, human in the loop Linux command agent. So there's 2 nodes. We allow the LLM to generate a command, and then we allow the LLM to execute a command. And then there's a check that says, should I do this or not? And this is the human feedback. So I'm going to build a graph and say, get the user prompt, generate the command, ask the user whether or not to execute that command, and then execute the command. Simple LangGraph. And this human in the loop pattern is something that you'll see a lot of with LangGraph. So here's my command node, generation command node. Given the user's prompt, just generate the Linux command based on what the user asks to do. And then this is the user check step. It's like, okay, this is the command that got generated. Should I execute this command? And then you're going to give it a response. And then you're going to ask the LLM, well, was it yes or no? Return no, else return yes. So you have to hope that the LLM will follow these directions and only do no or yes, because you're going to encode in your graph that message of no or yes is going to determine agent flow in your graph. So that's this check. And then if it passes this user check, then I just do an OS system and I invoke that thing. Okay, so I define the graph. I have these nodes. I attach the nodes with edges. I add a conditional edge here. And then I compile the workflow and I say, display this as a mermaid graph. And this is what it looks like. I start, I generate, I get the user's input, I generate the command, and then I conditionally figure out whether to execute it. That's what these dashed lines are. And it goes to the execution node, and then you're done. Okay, so then you run this thing. What's the size of the current directory in megabytes? And it's like, this is the command du-sh dot, and then print the first argument. And you're like, yeah, go ahead and execute that. It's not rm-rf, so I'm good. And then it's like 294 megabytes. And then find all files that begin with the letter A, and you say, should I execute this command? And you're like, no, and then it doesn't execute this thing. So that's like exercise number 8 in this week's lab. Okay, the last exercise in the labs for this week is a web assistant, and I mentioned this before. Spawn multiple agents to collect today's sports headlines. So you have a coordinator agent that says, figure out what the user is asking for and figure out which sub-agent to call. So if the user is asking for all sports headlines, then I'm going to kick off both the NBA sports headlines and the NFL headline node, collect all those headlines, and then return the result. If the user only asks for basketball headlines, it will only kick off this node, or football headlines and only kick off that node. Okay, so this is what it looks like. The route determines which agents to call. So this is like the supervisor, the coordinator. You get the user's request, decide whether or not sports news is requested, and then this is the instruction to the LLM. Reply with exactly one word, either NBA, NFL, or both. So it determines which branches to call in your graph. You invoke this, and note I'm doing asynchronous invocation. This is how I get concurrency. And if you don't like concurrent asynchronous programming, unfortunately, there's a whole bunch of it here, because it's just, that is the pattern that people are using. It makes no sense to block on an LLM or on a tool call. So almost everything that you see that's useful is done with asynchronous IO. So that's why this is here. And then if the decision is NBA, I send the NBA message to that agent, the NBA agent. Otherwise, I send it to the NFL agent. If it's both, so if the decision is both, then I send it to both things. And this gets you the parallelism. I send both messages asynchronously. Both agents kick off and run their code concurrently. Okay, so then what are these agents doing? These agents are super simple. They're just fetching the RSS feed for ESPN is the one that I found. There's an NFL RSS feed and an NBA one. You just fetch it and then extract it and then summarize it. So these are LLM calls. So again, these are all done asynchronously. So they'll execute when the data is available. And then this last thing at the end, this is your gather on the asynchronous IO. This collects all the results. So this actually will block and will only return when both of these are available. Okay.
Does ESPN do any like bot detection? You need to worry about that?
Well, that's why this is ESPN and not. I tried a bunch of other ones. I was getting blocked, and I'm like, I don't want you to just hit Oregon CTF, which is I don't block anything. But there were a couple, and then I was getting there's a bot. Like I don't want to solve their CAPTCHA. So yeah, that's why this is the RSS feed. Okay. Oh, so what I wanted to do was Corsical actually. So Corsical is very aggressive in terms of filtering bots, but they've got a better interface to get course data on Portland State's CS department than we do. Like the way they've indexed it and done the UI. So I'm like, oh, can you ask, when's the last time CS 475 got offered? And then like I was going to point it to Corsical, but then I found out they're filtering bots. In fact, our own site, pdx.edu, filters Python access unless you specify in your user agent a specific string. So yeah, PDX academic client / whatever. So yeah, even our own website, you have to actually prove that you're not a bot or you have a secret handshake. So this is important if you are doing one of these for your own. Yeah, you gotta like look at the, and the other thing is that some of these, like the fetch, so I didn't show you this code. Some of these don't follow redirects. So if you are using web retrievers and you're like getting blocked or getting 302s or you're getting all these kind of crazy codes, realize that your async HTTP client might not be following redirects or might not be doing the proper, it might be getting blocked by CAPTCHAs. So yeah, that's the short that's kind of why these are, those aren't.
And so you said it'll recognize when it's been updated, or is that like?
No, this is just polling.
Okay.
So, yeah. There is no push notification onto an agent, but you could do it like if you wanted a push. I don't know if agents, you could probably build a callback into your agent and execute on a webhook. but that would be, yeah, you could build that in your own homework, but there's nothing like that here. Okay, and then this is the code. So if you look at these agents, they're just fetching the feed and then extracting the headlines and summarizing it. So then this is going to be an LLM call done concurrently, potentially. And so that's what this is. It's like I fetch the content with HTTPX asynchronously, and then when that comes back, I do the extract and summarize, and this is the prompt that I give it. You know, one concise paragraph, and then only return that paragraph as a string. And I only look at like 12,000 characters. I want the whole thing. And then I invoke that and then return the response. Okay. And this is all done, again, asynchronously. And you see this on modern, like when you're interfacing with Gemini and ChatGPT, you see a bunch of stuff happening in the background asynchronously, concurrently. It's effectively what that thing is doing, is what this is doing as well. They're spawning off a bunch of tasks, collecting the results, generating the response. Yeah.
So in general, if we have like, think of comparisons like length, like using the train of thought kind of reasoning, this should be at least save us some tokens and hopefully be a bit more accurate in general. It's kind of forced into a certain thinking.
I think so if done right, but like you could easily do the same. Yeah, you could implement your same garbage pattern in the LangGraph way. It depends. Like you could build a monolithic node that does the exact same crud that it's done, or you could do it in a non-asynchronous way. You could easily write a non-asynchronous, a serial LangGraph application. In fact, that's what this was initially. And I was like, I probably should do an asynchronous one. And fortunately for this class, ChatGPT is so good at converting your serial code into asynchronous code that I was like, yeah, you do it. and then it worked. Well, ish. There were a couple of things I had to fix, but like it was pretty good at doing that. Okay, I should say there are a ton of other multi-agent frameworks. Now, I focused on LangChain and LangGraph because that's what I started with. But there's like Crew AI, BAI, the IBM Triad, the Google's got agent to agent. If you all want to explore these other frameworks, like I thought LangChain was going to be a winner, but if you don't agree with LangChain being the winner, go find the thing that you think is going to be a winner. And then if I actually believe you too, maybe I'll switch over. I do think I saw someone did a Crew AI project in my cloud class last quarter. I was like, oh, yeah, I could see why you would want to do that. So if that's something you want to do for this week, yeah, you're more than welcome to do. Try these other agent frameworks as well. Okay, the next thing I want to talk about is Langsmith. And there's just a tiny part of this week's lab with Langsmith. This is basically a debugging framework that makes debugging your application easier. And you'll see, like, man, going through traces of execution is super painful. Like, if all you're doing is dumping that out into standard out and then scrolling up and down, you're in for a world of pain. So Langsmith is there to make that easier. So what happens is you enable the service in your Python program. You create your account, you enable the service, the tracing in your app, and then it will stream the event data from your agent to their web server. And then it'll give you a very nice UI to poke in through there. You see the number of tokens consumed, you see the amount of time it took to do a call, you see the input, you see the output, you see all the tool calls. You can filter on the tool calls if you don't want to see any of the other stuff going through there. It's really well done, which is why, and it's free, at least for now. So this is what it looks like. So you're running your agent, and then you're like, oh, well, I want to see everything that my agent is doing. And you see it there, runnable sequence, terminal call, calls to the model, the generative AI model. You can see the actual trace, the React trace going through there. So I wanted you to see that in case it might be helpful as you're debugging your agent, especially if you're using LangChain. If you're using Crew AI, I don't know what they use for that. So here's an example. You can actually poke in to see the input of these different calls of the agent executor. And so you can see the input that you got, and then the result, which is here. It's like, look up Portland State University. This is like, I think in week 8 or week 9, one of your agents find the name of the website, look up its IP address, and then figure out what the name of the host that serves it. And this is where you can see that Portland State hosts their website on CloudFront with AWS. And you're like, oh, so it's chaining together a bunch of tools to figure out something about Portland State's website. And then you can trace execution. And actually, so you're like, oh, look up the IP. And then there's a tool that I call look up the name. Oh, no, it starts with the search, looks the name up, and then looks up the IP. And then there's actually more beyond this to actually get the rest of the answer here. Okay, questions about this? SQL injection. So one of the things that you're doing in your lab is that you're performing a SQL injection attack on the agent. You're trying to trick the agent into, I don't know if you know that XKCD, it's like Bobby drop tables. It's like she names her son a SQL injection string and it wrecks the school's database. So you're gonna do the exact same thing to an LLM agent. And I'm not going to actually go through the walkthrough of this. This is like in the web and cloud security class. If you do not know what a SQL injection is, I can point you to some labs, or you can go through this animation. But I don't think I want to go through all of it because some of you I know are in this, have done this class, and I don't want to go through there. But basically, what you're doing is you're taking in a username, and you're saying, I'm going to break the syntax. I know you're going to take my username and you're going to copy it into a SQL statement and then execute that SQL statement. But your SQL statement is delimited by single quotes. So what I'm going to do is I'm going to inject a single quote and you're going to say my username ends here. And then the rest of this is going to be interpreted as SQL. So you're going to be injecting a SQL statement. You're going to be injecting this as a username. And you're going to invoke a SQL injection attack on the agent, who is basically the natural language interface to your SQL database. And then you're going to see, yeah, we're in trouble here. Unless the agent somehow magically knows about all SQL injections and can drop them, we're in trouble. So, okay, but I don't want to go through this since it's already have got you for quite a long time here. I do want to get to the homework. So yeah, homework number 2 is build a bot, create your own custom LangChain agent, or if you're going to use other frameworks, you can create your own agent in these other frameworks. So the minimum, these are ideas. You can use an alternate agent type or architecture than what was used in the exercises. So in the exercises, we've done the React, but if you want to do some of the other ones, you're more than welcome to try those. I do want you to use one additional built-in tool or toolkit that's not contained in the lab exercises, and then to create one custom tool or toolkit. So one of the tools you can add is your own RAG application from this week, if you want that to be a tool that an agent can call. And then the last requirement, so this is optional, but then these are requirements. And then the other requirement is that you must have the terminal or the Python REPL tool in your agent, because in 2 weeks, you'll be penetration testing your agent and causing arbitrary Python and terminal commands to be executed as part of your assignment. Same submission method. Okay, so with that, I'm going to stop and allow you to get started on the labs.